All right. So let's look at pages 11, 12, and 13. Let me just say I am extremely excited to be back. Really, really, really excited. All right. Okay. I'm not sure where you left off with this, so I'm just going to give you answers to the whole page. So on page 11, A, a horizontal line. This is review from a position time graph would indicate that something is not moving on a position time graph. The speed is 0. If you have a straight diagonal line, that means you have a constant velocity. There's no acceleration. That is unit 2 material. You need to know that for tomorrow's test. Now, a curved line, this is the new stuff, means that the object is accelerating. And if you have a gradually sloped line, that means you have a slow constant velocity. That's what graph D over here is representing. That's a slow constant velocity versus a steep slope line, like line E, would indicate that you have a fast constant velocity.
Would you put the credit to slow constant speed or just say velocity?
You would have to say velocity here because it's a position time graph. If it were distance time, you could say speed. And then number 2, now we're going to look at the velocity time graphs. A are both graphs A and E. Letter B is graph D. Letter C is graph A and E. Letter D, there isn't one. There are no graphs which change direction. Letter E is graph B. Letter F is graph D. Okay. All right, letter G is graph D as well.
Oh, sorry, what was that?
D as in dog. Should be up there on the screen as well. Okay, number 3, letter A, a horizontal line means that you have a constant velocity. There's no acceleration. These are velocity time graphs now. A straight diagonal line means that you have an acceleration. Letter C, if you have a gradual slope velocity time graph, that means you have a small acceleration. Versus if it's steeply sloped, that would mean you have a large acceleration. Number 4. Okay, so let's go through these. A, the objects that are rest are graphs B and C, but this is only when they are crossing the time axis. So there are moments in time when they're not moving. Graphs B and C have that. Letter B, which object or objects are accelerating? That's graphs B, C, and D because they're diagonal lines. Letter C, which objects are not moving? That's the same as letter A, graphs B and C. But again, that's only when they are crossing the time axis. There are moments in time when the objects are at rest. Letter D, which objects are changing their direction? That's graphs B and C. They go from quadrant 1 down into quadrant 4 or vice versa. Letter E, which accelerating object has the smallest acceleration? That means you're looking for the shallowest diagonal line. That would be graph B. And letter F, which objects have the greatest acceleration? That means which is the steepest diagonal line? That would be graphs C and D. And D, I'm only looking at this first part, not this part here. There's no acceleration here, but this one and this one, those are parallel. So they have the same large acceleration there. And letter G, which objects are moving in the same direction as object E? They would have to be in the same quadrant at some point. Those are graphs B, C, and D. B, C, and D both start down here in quadrant 4, so they are beginning all in the negative direction. All right, any questions on page 11? All right, let's go to page 12. So we have these graphs. I want you to pick which graph goes with the description. So number 5A is graph E. 5B is graph B. C is graph D. D is graph A. E is graph C. Number 6, we had to draw these ticker tapes. So this one, if we are traveling to the right, would match graph A. which shows that the dots are getting closer and closer together as you read from left to right. That indicates the object is slowing down. That is what that position time graph parabola is showing us, that it's slowing down. Graph B is showing it's speeding up as it goes to the right. So again, I need an arrow pointing to the right, showing it's speeding up with these dots getting further and further and further apart. Graph C is showing it's speeding up but going to the left. Negative slope means it's going left, negative direction. So here's the arrow showing me I'm going to read this ticker tape from right to left. And these dots, as I read them from right to left, are getting further and further apart. Graph D shows it's slowing down as it goes to the left. So again, I have my arrow on here showing how I'm going to read this from right to left. And these dots are getting closer and closer together. Number 7. All right, same thing, but now for the velocity time graphs. So graph A is traveling to the right and speeding up. There's my arrow to the right with the dots getting further and further apart. Graph B shows it's slowing down as it goes to the right. So these dots are getting closer and closer together as I read it from right to left, from left to right. Graph C shows it's slowing down as it goes to the left. So the arrow showing it going left. As I read this from right to left, I should see these dots getting closer and closer together. Graph D shows it's speeding up as it goes to the left. So there's an arrow to the left, dots getting further and further apart as you read this from right to left. Any questions on page 12? All right, let's go to page 13. And I'm not sure which ones I had on the video with you, but this first one, constant velocity, this is your test tomorrow. If we are moving in the positive direction, that means our velocity direction is positive. So on a position time graph, I need a diagonal line with a positive slope and a horizontal line on my velocity graph up in quadrant 1 above the horizontal axis. If I have a constant velocity as I move in the negative direction, that means the velocity direction is negative. So my position graph should be a diagonal line with a negative slope, and my velocity graph should be a horizontal line down in quadrant 4. Again, these two sets of graphs are on tomorrow's test. Now, let's talk about constant acceleration. This is not on tomorrow's test. This will be your next test in about a week. The velocity direction is positive because we are moving in the positive direction. But since the acceleration and the direction of motion are the same, both positive, that means you're speeding up. So our position graph should have a positive slope but getting steeper, and our velocity graph should be above the time axis, diagonal line with a positive slope. Now, if I do a constant positive acceleration in the negative direction, velocity is negative. That negative direction means I'm moving in the negative direction. Since the acceleration and velocity are opposite in directions, that means I'm slowing down. Slowing down means my position graph has to get shallower, but because I'm traveling in the negative direction, the parabola's got to go down. It's got to go down and get shallower. My velocity graph needs to be down in the negative quadrant, quadrant 4, and it's a diagonal line with a positive slope because I have a positive acceleration. The next one, constant negative acceleration, moving in the negative direction, so my velocity direction is negative. Notice the acceleration and the velocity are the same sign, so that means I'm speeding up. Speeding up, going to the left, in other words. That means my parabola for the position time graph needs to go down and get steeper. My velocity graph should be down in the 4th quadrant, diagonal line with a negative slope. The negative slope means negative acceleration. And finally, if I have a constant negative acceleration, that means my velocity is positive because I have the positive direction, and I am slowing down because the acceleration and the velocity are opposite signs. So my position graph has to go up and level off. That's what indicates slowing down. Positive direction means the graph is going up. The velocity time graph has to be up in quadrant 1 because I'm moving in the positive direction. But since my acceleration is negative, I need a diagonal line with a negative slope. It does not go down into the 4th quadrant. All right, any questions on these graphs? All right, let's take out your Chromebook and let's take your quiz. You can use that homework to help you with today's quiz for Unit 3B. And when you complete the quiz, I'll ask you to put your Chromebook away. Good luck. And when you complete the quiz, please put your Chromebook away. You can then take out the review assignment that was due today for Unit 2. Where are you still working? All right, ladies and gentlemen, let's look at the Unit 2 review, which was completing your packet, first of all, for Unit 2. Okay, let's look at that first. I want to give you answers to all those pages at the end of the packet. And then I did ask you to complete the problems on the Unit 2 review worksheet with trig and the head to tail stuff. That was to finish this. I don't think that the video did that. It did, I think, the front, but not the back. So you had to finish the back. We'll go over that as well, since that will all appear on tomorrow's test. Tomorrow's test, we only have a single class period, so that's all you're doing. For the test tomorrow, please make sure you bring a pen, a pencil, your own ruler and protractor, and your scientific or graphing calculator. Those are the items you need for the test. You won't need anything else here tomorrow for that single period test, okay? Any questions for me? All right, let's get going. In your Unit 2 packet, so the first page of the review was with this, correct? Am I right? Yes? Okay, so let's start looking at that page. So the first one, you had to kind of complete all of the columns that were not given to you. So what I did here on the first one was I labeled each of these line segments given to me on the position time graph, segments 1, 2, and 3. So over here on my velocity time graph, segment 1 would look like a horizontal line up in the positive quadrant. Segment 2 would be a horizontal line on the time axis. And segment 3 would be a horizontal line down in the fourth quadrant, negative section. Now, if I were to describe what's happening, segment 1 is an object traveling to the right with a slow constant speed. Line 2 is an object that is not moving, it's stopped. And line 3 would be something traveling to the left with a fast constant speed. I know 3 is going faster than 1 because it's steeper. And I know it's going left because that has a negative slope. That one's a positive slope, so it's going to the right. Now, if I were to make a motion map, it would look something like this, with an object traveling to the right, arrows the same length, then it stops, and then arrows to the left that are longer. The number of them doesn't matter. The number of dots doesn't matter. You can't tell because we don't have actual time values on the time axis to tell us how many dots to put on that motion map. All right, let's look at the second one. This one I gave you the velocity graph. So there was a horizontal line segment here. I'm going to call that segment 1. This is segment 2, and the horizontal segment 3 is on the time axis on the velocity graph. So the position time graph should have a steep negative slope for segment 1, a shallower positive slope for segment 2, and a horizontal line segment for segment 3. Line segment 1 is an object traveling to the left with a fast constant speed. Segment 2 is an object traveling to the right with a slow constant speed. And 3 is an object that is not moving. It's stopped. So if I were to make the motion map, we'd have these long arrows to the left. Then it would stop, quickly change direction, and then be stopped for a longer period of time. All right, let's look at number 3. The position time graph has 3 segments, 1, 2, and 3. So my velocity time graph would have a horizontal line segment down below the time axis, pretty close to the time axis. Segment 2 is a horizontal line on the time axis, and segment 3 is a horizontal line well below the time axis. So line segment 1 is an object that's going to the left with a slow constant speed. 2 is not moving, and 3 is traveling to the left with a fast constant speed. So my motion map should show something traveling to the left with small arrows that are equal length, then not moving, so several dots lining up with each other, and then several arrows pointing to the left that are longer. Same length on each of those. All right, let's now go to this one. This one I gave you the velocity graph. So segment 1, 2, and 3. Segment 1 on the position time graph would be a horizontal line above the time axis. Segment 2 should be a steep slope positive diagonal line. And 3 should be a fairly shallow sloped diagonal line that's negative. So 1 is not moving. 2 is traveling to the right with a fast constant speed. and 3 is traveling to the left with a slow constant speed. So to show this on a motion map, we have several dots which line up with each other, so that shows no motion. Fast constant speed to the right means I need several arrows, same length, pointing to the right. And then instantly changing to slow constant speed to the left, I should have several arrows pointing to the left, equal length, but smaller. The exact number doesn't matter because I didn't give you time values. All right, let's go to the next page. These I gave you the descriptions. So on this first one, we have to show something traveling with a constant positive velocity for 4 seconds, then stopping for 2 seconds and returning to our initial position in 2 seconds. So let's start with our position time graph. I should have a positive slope diagonal line from 0 to 4 seconds. Then a horizontal line segment, which goes from 4 to 6 seconds. And then a negative slope diagonal line, bringing us back to the position of 0 at 8 seconds. These needed time values. Now, my velocity time graph should show 3 horizontal line segments. One up in the positive quadrant, one on the time axis, and one well below the time axis. This one should go from 0 to 4 seconds. That's 4 to 6. And this one is 6 to 8 seconds. So my motion map would look like this. Arrows to the right, which are fairly small, from 0 to 4 seconds. Then we have to stop between 4 and 6 seconds. And then we need several arrows here to the left that are longer from 6 to 8 seconds. This is traveling faster because it's steeper than that one. All right, let's look at the next one. What did I give you here? I gave you the motion map. So let's start with the description. This description for this motion map is that we have an object traveling to the left with a constant speed for 2 seconds. It then stops for 2 more seconds, and then it moves to the right with a constant speed for the next 4 seconds. And it returns back to its initial position. You see how those 2 dots are lining up? That's getting us back to our initial position. So if I were to draw my position time and velocity time graphs, my position time graph should have a negative slope diagonal line, a horizontal line, and a positive slope diagonal line. These 2 points should have the same y coordinate. The first diagonal line is from 0 to 2 seconds. The next is from 2 to 4 seconds, and the next is from 4 to 7 seconds. And then over here, my velocity time graph has 3 horizontal lines. The first one down in the negative quadrant from 0 to 2 seconds. The next is from 2 to 4 seconds on the time axis. And the last is from 4 to 7 seconds up in the positive quadrant. All right, so this one has 2 objects that are traveling. So our position time graph should have 2 diagonal lines, A with a diagonal line that starts at positive 10 meters, and the slope of that diagonal line should be negative 2 meters per second. Line B should start at the 0 meter position and have a positive slope of positive 3 meters per second. So B should be steeper than A. My velocity time graph shows A below the time axis at a y-intercept value of negative 2 meters per second. And B is a horizontal line up in quadrant 1 with a y-intercept of positive 3 meters per second. And my motion maps look like this, where object A is starting at 10 meters with 2 arrows to the left at 2 meters per second. Actually, the number of arrows really doesn't matter. You could have had multiple. And then B is starting at the 0 meter position with arrows pointing to the right, which are 3 meters per second in length. Okay, the last one, we were given this motion map, and you can see I labeled the times on there. So A is traveling for 4 seconds, but B is only traveling for 3. So object A is starting at the origin. B is starting ahead of it. So that's why B's y-intercept is above A's. They are both traveling with the same speed to the right. I know that because all the arrows are the same length. So these 2 lines need to be parallel with positive slopes. A and B here are going to be the same horizontal line on the velocity time graph up in the positive quadrant because they have the same velocity to the right. And our description, A is starting at the origin. It's moving to the right with a constant speed. B is starting to the right of the origin, moving to the right with the same constant speed that A has. All right, any questions on those 2 pages where you had to kind of match up all those different descriptions for the same motions? All right. Then let's look at this page, Unit 2 review. So first thing I wanted you to do with this position time graph is determine the average velocity. So the average velocity would be the slope of this graph. That is the displacement or change in position over the time. So I see it ends at 60 meters. It started at 10 meters, and that's happening over a 6-second time period, which gives us a positive 8 meter per second average velocity. You do need the positive sign on it because velocity is a vector. It needs to include the direction, which would be to the right, positive. Letter B, write a mathematical equation to describe this motion. So you know that it's going to start with y equals mx plus b, but then you had to make it get specific to this particular graph. So what's on the y-axis? Position, x. What's the slope? It's positive 8 meters per second. What's on the x-axis? Time, t. And then I'm going to add the y-intercept, which I can see is 10 meters. So position is positive 8 meters per second times time plus 10 meters. That is the equation for that graph. Now we're showing you this velocity time graph. I want you to first start by describing the motion. From 0 to 2 seconds, the object is traveling to the right with a constant velocity of positive 4 meters per second. From 2 to 3 seconds, the object is traveling to the left with a constant velocity of negative 3 meters per second. And then from 3 to 5 seconds, the object's at rest, or it's not moving. Now draw the corresponding position time graph and number the x-axis. So here is my position time graph. I have to go from 0 to 5 seconds. From 0 to 2 seconds, I should have a positive slope diagonal line whose slope is positive 4 meters per second. From 2 to 3 seconds, I need a diagonal line with a slope of negative 3 meters per second. And from 3 to 5 seconds, I need a horizontal line. Now, I can label the position axes because I can determine what my positions are at each of these by calculating the areas under these graphs between the line and the time axis. So I'm going to do that with part C, which asks me how far did the object travel from 1 to 2 seconds? Well, I can either do the area or I can use my velocity is displacement over time or speed is distance over time. So 4 meters per second times 1 second means that it moved 4 meters between 1 and 2 seconds. So the total displacement would be found for this entire graph. So I'm doing it first from 0 to 2 seconds. 4 meters per second times 2 seconds means that I moved 8 meters to the right. And that's how I get this value right here of positive 8 meters for that y coordinate at 2 seconds. Now I'm going to do it for the next horizontal line from 2 to 3 seconds. So that would be negative 3 meters per second for 1 second. That means I'm going to the left for 3 meters. Well, left 3 meters when I start at 8 meters brings me to the 5 meter position. And then from 3 to 5 seconds, my velocity is 0 meters per second. I'm there for 2 seconds. So I'm not moving at all. 0 meters. Now to come up with my total displacement, I'm going to add these values. Positive 8 meters added to negative 3 meters added to 0 meters gives me positive 5 meters or 5 meters to the right. Okay. Any questions on that page? All righty. Last page then here, number 3. This was all guess method. Determine the average speed with the information given. So to do that, I'm going to do the speed is the distance over the time. To get the distance traveled, he goes 1,920 miles out and back. So I have to add those two distances together and divide by the total length of his trip, which is 64 hours. So I take those numbers, I divide out, and with 2 sig figs, I get 60 miles per hour. What's his average velocity? It's 0. That's because his position did not change. He started at home, he ended at home. The displacement is 0 miles. And he did that in 64 hours. So 0 divided by 64 is 0. Chaudhry? Yeah. Okay, because if I want speed, I need total distance traveled. Out and back. 1,920 miles out, 1,920 miles back. 32 hours out, 32 hours back. You're welcome. Okay. C, compare the two values. Explain any differences. Well, the velocity is 0 because he wasn't displaced. He started and ended in the same location. Number 4, consider this velocity time graph. We have 2 line segments on there, segment 1 and 2. Describe the behavior in the graph. So for segment 1, the object is traveling to the right with a fast constant velocity. Line segment 2, the object is traveling to the left with a slow constant velocity. Don't worry about letter B. But if you did, this is what it would look like, something like that. Number 5, your test tomorrow won't test you on motion maps. It's going to test you on ticker tapes, those dot diagrams. You know the difference, right? The one ticker tapes don't have the arrows on the dots. Just can you draw them to show what it's got to show? Those are a little easier. All right, number 5, you have the race car traveling at 95 meters per second. How far does it travel in 12.5 seconds? Okay, so my givens here. My speed, V, is 95 meters per second. The time is 12.5 seconds. When I ask for how far, that means I'm looking for a distance, D. So to do this, we're going to start with V is D over T. So that means the distance would be the speed times the time. Now I'm going to plug in. So that's 95 meters per second times 12.5 seconds. I need 2 sig figs on my answer. So that should have been rounded to 1,200 meters. Now you have to do your check step. You're going to check the equation we plugged into. D is VT. What units is D measured in? Meters. We believe that's meters. Speed is meters per second. Time is seconds. Notice that the seconds end up canceling, leaving me with just meters, which is what I expected. That's the dimensional analysis step. All right, any questions on that? That finishes the Unit 2 packet, correct? Okay. Could you find that other review worksheet with the trig stuff, ruler protractor on the front, which the video, I think, went over how to do all 3 of those, if I remember right? Yes? Okay. So let's look at the back. Am I correct? The video did one of those for you? It did 4 for you, so you had to do 5 and 6? Okay. So let's go through how this is done. This is the trig stuff. So everybody should get exactly the same answer. There is no leeway on these answers at all. Okay. So you're going to go 60 meters west and then 80 meters south, calculate the displacement. Notice it says calculate. It doesn't say draw it with a ruler and a protractor. So I'm sketching it out first so I can see that I went 60 meters west, that's left, and then 80 meters south. So my displacement is down here in quadrant 3. So that means the final direction you give should be something between 180 and 270 degrees. To come up with the magnitude of the displacement, you're going to use Pythagorean theorem. A squared plus B squared is C squared. So the displacement's magnitude is 60 point meters squared plus 80 point meters, that quantity squared, then take the square root, and that gives you 100 point meters. We keep precision when we have an addition sign in there. So since these all went to the ones place, so does that. So if you just wrote 100 meters without the decimal point, you're going to lose a point on your test tomorrow for precision, sig figs. Make sure you follow the precision, sig figs. Now, how are we going to get the angle? We're first going to find the angle inside the triangle by doing the inverse tan of the opposite over the adjacent side. That's always the y side over the x side of the triangle. The y side is 80 point meters. The x side is 60 point meters. So do the inverse tan of 80 point meters over 60 point meters. And your calculator is going to give you 53 degrees when you do that. You round to the nearest degree. So now, when I look at this picture, I can see that the angle I need is from here all the way to there, where the angle I found is just this little part of that large arc. So I'm going to add 180 degrees to that to put it in the correct quadrant, which gives me an angle of 233 degrees. So my final answer for this problem should be 100 meters at 233 degrees. Make sure you put a degree sign after this. Otherwise, it is assumed to be radians. 233 radians is not the same as 233 degrees. So make sure you put that degree symbol. That's a unit. Any questions on number 5? All right, let's look at 6. Bloodhound is following their scent through the woods. They go 9 meters east and then 12 meters south. Calculate the displacement. So starting with my sketch, this is what it should look like. Arrow to the right, 9 meters. Then an arrow pointing down, 12 meters. My displacement is from the origin to that end point. This is in the 4th quadrant. So starting with finding the magnitude of the displacement, I'm going to do this a squared plus b squared equals c squared. So 9 meters, that amount squared, plus 12 meters, that amount squared. Then take the square root, gives me 15 meters for the magnitude of the displacement. Now to get the angle, we're going to do the inverse tan of the y over the x to come up with the angle inside the triangle right here. So that's the inverse tan of 12 meters over 9 meters. You get an inside angle of 53 degrees. Notice that the angle want starts at the positive x, rotates around the origin counterclockwise till we get to the displacement arrow. That angle we want and the angle we found together form the full circle, 360 degrees. So you got to back up by the 53 degrees to get your angle, which means you're going to subtract 53 from 360 degrees, giving you a direction of 307 degrees. So the final answer to that problem is 15 meters, 307 degrees. Okay. Any questions? Yes, please. So with zeros. So in this question, do you see how I have a point after that 0 and a point after this 0? You need to make sure you have a point there too then. Okay. For number 6, yeah, because there's no zeros, you don't have to worry about a point. If you wrote 15 point meters, it's the same thing. That's fine as well. Anything else? Yes, Miriam?
I got 53 for the angle, but I don't know why you added 180.
For question 5? Okay. This is down in the 3rd quadrant. So my answer has to be between 180 degrees, which is left, and 270 degrees, which is down. The angle we found is this part of the large angle we're looking for. So you just found this little arc right here. From here to there gets us the 180. So that's why we're adding 180 to the angle to give us the proper quadrant. Anything else? Okay, go ahead, take your break. When you come back, we're going to do a lab to review more of this. I think so. I got to see how I'm feeling by the end of the day. The thing that's been happening to me is I'm starting to get really tired. So if I'm but then what I'll do is I'll post something to say I'll have a Google Meet tonight from like 6 to 7, 7 to 8. I would email the whole class to say. Otherwise, if I don't email, I would. Okay? Does that make sense?
Yeah. So email if you're
Or post something on Google Classroom. That's the other thing I can do. Just put a post. Yeah. And say, here's how you join me.
Yeah, I like to go.
Yeah. Right. Those are
I get it right. You get it right. How are you? I remember a lot.
This one?
Doing it last year.
That's
Figure out what it is to this or I just have the scan. It looks like it was 6:30. No, I was 6. I had the lowest. Yeah, I did. You could tell.
Oh, you said.
I think it's Thursday or Friday. I'm getting
Sorry? Yeah, tomorrow, Mr.
I'm not, my dad told me not to.
Yeah. So you check the professor.
I was just gonna read it. It's like you, I guess like at the same time they broke with your arms. It's like after they got the order from the dude, that's so rude.
In Great Escape, there's an underground, right? The underground course.
I can't.
Wait, what was the actual answer?
I just thought it-
I thought it said the concourse.
That's how I was feeling too, same thing, I was like, yeah, well, just take your time.
It's not that hard.
You're welcome.
It's not that hard.
Okay, ladies and gentlemen, I need you to do me a favor and put everything away right now, please. Clear your desk. We need desk space for this lab. Eventually, all you're going to need is a pencil, a reference table, and a calculator for the lab. We're going to do this together, so that way you can get it all done and turned in before you leave today. It's really reviewing a lot of information from Unit 2. So it's a good lab to do before we take our tests, right? To review some things about constant velocity and constant speed. You can see that the title of this lab is Average Speed versus Average Velocity. So we're going to try to hit on the concepts of position, distance, displacement, speed, and velocity, knowing what's the same about them and what's different. Now, I'm going to be placing you in groups for this. And I need to put some tape down on the desk. And when I do that, whoever is near that piece of tape, I'm going to ask you to write something on the piece of tape. You do need to write now to clear your desk of everything but a pencil. Everything has to be off the desks because we're going to be using the desk space for things to collect data. So you do have to clear everything off your desk. Drink bottles, everything. Please put number 1 on this. Put 2 on that. And then definitely you can make sure to put 3 on this. Okay. Alex, go ahead, put a 1 on that. Josh, put 2 on that. And then I want you to put a 3 on that piece of tape. Okay, 1, 2, 3. Let's start with here. Here, I put a 1 on this, right? Let's do it up here. 1. And you're going to put a 2 here. And then you also need a 3 on that piece. Let's put a 1 on this, please, Janicia. I'm going to put 2 on this. And 3 on this. Shiny ashes for your receipt. We're going to put in 1 on this here, 2 on this here, and 3 on this. Let's do a 1 on this piece of tape. We need a 2 on this piece of tape. And 3. Okay. Remember these lab a while ago? Okay. So what we're going to be doing is this. Let me draw this. Oh, lovely. I'm not doing that right now. Of course, it wants to update right in the middle of class. That's not going to happen. Okay, you've got 3 pieces of tape labeled 1, 2, and 3. What I'm going to ask you to do in a minute is measure with a meter stick. I'm going to break you into a group, and with your group together, I want you to measure the distance from 1 to 2. We're going to call that the length, and then you're going to measure the distance from tape 2 to 3. That's going to be what we call the width, W. Okay? So in terms of what you're going to do with those is you're going to record them on a piece of paper. We give each of you the sheet. So I'm going to have the 4 of you work together in a group. 1, 2, 3, 4. The 4 of you will work together. 1, 2, 3. The 3 of you will work together. Go ahead and put your name on top of this. 4. The 4 of you are going to work together. The 3 of you are going to work together. And I have the 4 of you work together. 1, 2, 3. Each group is going to be given 2 meter sticks, so you can make these 2 measurements, all right? And let me give you the meter sticks. We do this one step at a time. Just measure those distances. And I'll tell you what precision I want you to measure to. So why don't you guys measure the distance from 1 to 2? You guys measure the distance from 2 to 3. How about the 2 of you measure the distance from 1 to 2, and the 2 of you measure the distance from 2 to 3. Just work together. Get 1 to 2 and 2 to 3. I don't think there's 2 or 6 of you. You should measure from 1 to 2, and you 2 should measure from 2 to 3. If you need more than 1 meter stick to do it, you can also do that. So here's 2 meter sticks. You measure between 1 to 2 and 2 to 3. And the same thing. 1 and 2, 2 and 3. You've got 2 sticks. And when you do this, folks, what does it say? Measure to the 100th of a centimeter. That is the correct precision of those meter sticks, okay? And once you have it, we're going to record it in the first data table on the page. You can go like from the middle. Go from the middle, please. Work together, and when you have them, write them down.
I got 90. Yeah, it'll be one.
Measure to the 100th of a centimeter, please. So every measurement you have should go out 2 decimal places. One stick, remember, is 100 centimeters. So if it goes beyond 1 stick, just add 100 to whatever you have. So I'm going to make up some numbers. It's like something like 104.62 and maybe 31.85. I don't know. Just making up numbers.
So that's minus 10.
So if you look up at the screen, you'll see that my measurements have gone to the 100th of a centimeter, as should yours. Right? Out 2 decimal places. That is the 100th of the centimeter. I just made up numbers though. You saw I didn't go around and measure anything. I just said, these numbers sound good. You actually measured yours. Yes? Okay, now let me show you what you're gonna do. You don't need the meter sticks anymore, so let me come and collect those. You guys are all set? Thank you. Watch out, Ryan. Can you grab those?
Yeah.
Thank you. Guys all set? Excellent. Thank you. Let me describe what we're going to do next. So each group is going to be given one of the buggies. You're going to turn it on so it goes in the direction. And what we're going to try to do, gentlemen, can you help me out with this? Where's 1 and 2? 1, 2, and 3. All right. So what we would do, the buggy, you're going to turn it on and you're going to start it at tape 1. You're going to let it travel along the length of the desk until it gets to tape 2. And then you're going to quickly turn it so it gets to tape 3. Now, someone in the group is going to need to time that motion with their Chromebook stopwatch. So one person in the group who's not near the tape should grab their Chromebook, go to Google, and open up a stopwatch. Okay, one person per group. And what you're going to do, look down here in data table, the second table. It's asking you for the time for 3 trials. Do you see that? We need 3 trials. So you would start the stopwatch when the person puts the buggy down at position 1. Someone who's next to tape 2 is going to quickly turn it. And then you stop the stopwatch when the person at tape 3 picks it up. If you need to move around to help make that happen, get up out of your seats and do that, please do. But time it 3 times and record the 3 times there, and then we'll talk about how to do the average after that. Okay? Questions on that? Yes?
Do we stop it?
No, 3.
No, at 3.
You do it at 3. You're going to start it at 1, let it go to 2, quickly turn it so it goes to 3. So you start it the moment you place this down on the desk at 1, and you stop it the moment you pick it up at position 3. Please make sure they don't fall off the desk, because that would break it. And I have no extras of these. I would have to buy some for next school year. We have no money right now to buy any replacements. Okay? All right, let me come around and give everybody a buggy. Each group a buggy. Where's 1? Who is 1? Now, when you turn these on, this has a bi-directional switch. So if you want it to go in this direction, you turn the switch and push it in that direction. So it goes in the direction.
Ready? 3, 2, 1.
Bi-directional switch. So if you want it to go this way, you have to switch in that direction. Okay. And then, guys, same thing. You want it to go this way, so you push the switch in that direction. Get those 3 times.
Yeah.
5.95.
Once you have all 3, let me know. You can bring your buggy up and put it back on my cart for me. Once you got all 3 times, please bring the car up front, and then we'll talk about how to do the average once everybody's ready. You can then put your Chromebook away once you have all the times. You won't need it anymore. And then all you'll need for the rest of this lab is the worksheet, pencil, reference table, and calculator. All right, so let's talk about how to do the average. The first thing I want you to do is add up the 3 times that you just recorded. Go ahead and add those up. Whatever your numbers were, I'm adding mine. And then you take that sum and divide it by 3. And you need to round the average. Remember, we always round the average to the same precision as the actual data. So since my data goes to the 100th place, I need to round to the 100th place. So my average would be 5.73, and I would record it there. Okay. Check with your partners in your group. You should all be getting the same average. Okay, Elisa, let's put your Chromebook away. Sydney, thank you. Put it away. Okay. Just reference tables and calculators and pencils for the rest of us. Okay, everybody all set? All right. Let's start with question 1. This says measure. We're going to correct that. We want this to be calculate the displacement that the constant velocity car traveled to the nearest 100th of a centimeter, and then we'll convert that to meters. So let's make just a little sketch again. It went from 1 to 2 to 3. We had our length here. We had the width there. Where is the displacement in that picture? Yeah, from 1 to 3. That arrow right there is the displacement. How are we going to calculate that? What equation should we start with? Miriam? Yeah, so let's start with a squared plus b squared equals c squared. Now let's say L is A and W is B, so the displacement would be C. All right, so let's go ahead and plug in your numbers. I'm going to use my numbers, my made up numbers from up here. You use yours. So my length would be 104.62 centimeters, which I need to square, plus 31.85 centimeters, which I need to square to give me my displacement squared. So go ahead, do your math to find the displacement in centimeters. For your numbers, don't use mine. And then check with your partners to see if you get the same answer. You keep precision. So you should get that to the 100th place. Round it to the 100th place, whatever you and your group have. Make sure you and your partners in your group agree on what that answer is. Everybody all set? Okay, now, next thing. Your number and mine are not going to agree, right? Because I'm using fictitious numbers. You have to use your group's numbers. The next thing I want you to do is convert that to meters. Let's just talk about what you do to get meters when you have centimeters. You don't have to show it to me. What do? Do you know how many times you're going to move the decimal place? No, that would be if you had millimeters. Your reference table will help you with that. Look at the power of 10. What's the power of 10 on centi, Khalees? Yeah, you're going to move it 2 to the left. The negative means go left. So that means if I move the decimal 1, 2, I would get my number. I'm going to keep all those digits. That's my answer in meters. Okay, move your decimal 2 places to the left. Keep all the digits. That's your answer in meters. Now, that's only half the answer you need. I want you to tell me what the angle is here in the triangle. What is the angle of that displacement? Do you remember how you're going to find the angle in the triangle? What trig function do we use? The tangent. So to get the angle, we're going to do the inverse tan of the opposite over the adjacent side. Which side is opposite in this triangle? The width. So that means I'm going to do the inverse tan of the width over the length. So that means I'm going to take the inverse tan of my width. You're going to plug in yours, 31.85 centimeters, and divide it by your length, which is 104 points. For me, 104.62 centimeters. My centimeters cancel. Now, I want you to get that angle to the nearest degree, please. Do it with your numbers, not with mine. You and your partner should agree on what that angle is. Go to the nearest degree. Go to the nearest degree. Everybody in the group should be doing it with their calculator to make sure you know how to do this for tomorrow's test, because you will have to do this on tomorrow's test. I just made up numbers, so my answer may be completely different than yours, right?
Yeah, our one should be the main thing. Yeah. So it should be
And then you can give me your final answer boxed in. The amount in meters, comma, the angle in degrees. Box that in, and that is your displacement. Yes, Nikolai. Because really what we would be doing, and then we have to know on this, is if we look at it this way, we just send an arrow, what we're going to do. Okay, right now, I just want you to find that particular inside angle between the length and the displacement. Okay. Yes, Kiara? Which one? This? Okay, because I wanted it to the nearest 100th of a centimeter. This is the 100th of a centimeter, right? There's my 100th of a centimeter. So we don't drop digits when we go from centimeters to meters. We keep all the digits that are there. Yes, please. Because I just told you which one I want you to pick. In the future, you're always going to do it you always go from the positive X direction, counterclockwise around the origin. Okay, this one, I'm telling you where I want you to come up with the angle. Because even though our picture looks like this, it could have looked like that. That looks more like what we're used to seeing, something right and then something up, and then it would go like that. So that would be the angle we would look for. Okay. Okay. Everybody good? Okay, let's go on then to question 2. Question 2 says, calculate the distance the constant velocity car traveled and then convert that to meters. So with these values that you have for this picture, how are you going to come up with the distance? what are you going to do to find the distance it traveled? If the car went from here to here to here, Ryder, just add them. So to get the distance, D, without the arrow, you're going to add the length to the width. That is your equation that you would use to calculate your distance. Just add the length to the width value with the units. So the length that I had was 104.62 centimeters. I'm going to add that to the width that I made up, 31.85 centimeters. And that's going to give me an answer for the distance in centimeters. We keep the precision, so you're going to keep the answer out to the 100th of a centimeter. But then I want you to convert it to meters. And you remember how we just did that in problem 1? What did we do in problem 1 to get the number of meters, Miriam? To the left, that's right. And we don't drop any digits, so that would be my answer for the distance. Move it 2 places left, keep the digits, and that will give you your distance. Any questions so far? Okay, let's go to number 3. This is a guess method question. I want you to find the average speed of the car. In order to find a speed, what do you need to know? What are your givens when you need to find a speed? 1, you need to know the distance and the time. Where are we going to get the distance? Where are we going to get the distance from? Gianna, where am I going to get the distance from? Yeah, it's your answer to question 2 in meters. And where am I going to get the time from? Where am I going to get the time from? Alex, what do you think? Yeah, the table. It's the average in the second table. Use the average value, please. Use your average time. 5.73, not 5. Okay. What is unknown is the speed. Speed is letter V. What equation are you going to write to calculate the speed? Miriam? Yes, the speed is the distance over the time. V equals D over T. Now do your substitution with units. And now you're going to calculate your answer. Please get an answer with proper units and significant figures. You should confer with your partners to make sure you are getting the same answer with the proper number of significant figures. I'm not going to require you to do a check step right now. Correct. Mine has 3. 5.73 with the Pacific rule would have 1, 2, 3 sig figs in that order. If yours is different, like if you got an average time of 10.26, that's 4 significant figures, you would have to round to 4. Adding or subtracting, you would go to the hundredths place. Not counting sig figs. You would do precision. But it's not. It's division. Okay. We good? I go on? All right. Number 4 now wants the average velocity. What do you need in order to find a velocity? Miriam? You need a displacement and time. Where are you going to get the displacement from? Flavia, can you tell me? Yeah, it's your final answer to question 1. Whatever you boxed in for question 1 is your given for the displacement in question 4. Notice I'm including the direction. Where am I going to get the time? It's the same time. The average from your second data table. The unknown is average velocity, or V with the arrow over the top. Now, how do you calculate a velocity? What are we going to do to find this velocity? Nikolai? Yeah, so the velocity, V with the arrow, is the displacement, D with the arrow, over the time. So we can then do our substitution with units. And when you do the math, you're not going to divide the direction by the time. You just take the displacement's magnitude and divide it by the time. Again, you need to round your answer to have proper significant figures. And then the direction on this velocity should be the same as the direction of the displacement. So you're just going to carry that angle measure down. And I need 3 significant figures because my time had 3 significant figures. My displacement had 1, 2, 3, 4, 5 sig figs. So I have to go with the fewest number of sig figs when I divide, which would be 3 for me. My time had 4 significant figures. I would need 4 sig figs on this answer. Please confer with your partners in your group to make sure you're all getting the same thing, including the direction. Okay, how are we doing? All right, let me explain what you're going to do in number 5. In number 5 says, what's the difference between an average speed and an average velocity? There are 2 things that are different. So you need to give me 2 separate, different answers in question 5. Let me give you a hint as to where you're going to look for this. The first thing I want you to do is look at the givens that you used to give you the speed and the time. There's a difference there. You see a difference in what you used for givens? That's one of the differences. The other is with the answer that you got. There is something different, and I'm not talking the number. There is something else that's different about these answers. Those are the 2 things I'm looking for. Do you understand what I mean? I gave you like a huge hint by explaining this without just saying, figure it out. Good luck. One of the differences comes with the givens. The other is in how we expressed the answers. So please talk to your partners, figure out what those 2 differences are, and explain each of those here. And then the lab is done. When you have finished the lab, collect it up as a group, and then you can turn them into me. All right. And that will complete our class today.